Hello everyone, welcome to this lesson. So in this lesson, we're gonna deal with another class of formulas called the high accuracy finite different formulas. And the reason I'm distinguishing and calling them high accuracy because it distinguishes them from the formulas that we dealt with thus far. The ones that we dealt with thus far are the conventional finite different formulas, or the ones that are commonly used. And those are the forward, backward, and centered for the first derivative, and of course the forward, backward, and centered for the second derivative. Now, the idea here is can we take these formulas and make a more accurate version of them? And the answer is yes. And so what I'm going to do in this lesson, I'm going to take the most accurate formula in terms of the first derivative, which is the centered, and the most accurate formula for the second derivative, and I'm going to create their associated or their corresponding centered for the high accuracy, and I'm going to see if it tops the formulas that we have that are the most accurate up to this point. So that's the purpose of the lesson. So if you remember with the first derivative, what did we do? We truncated the Taylor series at the first derivative here, and with minor manipulations, we came up with these three equations, right? So with the high accuracy, what I'm going to do is I'm going to actually add another formula or another term from the Taylor series. So I'm going to include the term of the second derivative. And this is, we're going to formulate the forward finite difference because it's easy to understand. Then I'm going to present what the centered would look like. So this is the forward finite difference because it's xi plus 1 and xi. So we have this truncated version down here. So what I'm going to do is I'm going to take this equation and I'm going to rewrite it in terms of the first derivative. And when I rewrite it in terms of first derivative, I have this version down here. Now, usually or always, these equations are defined only in terms of the function, and this is the idea of these formulas. If I know only the function, can I get an approximation for the derivative? But you can see that this is defined in terms of f of xi plus 1, f of xi, and also the second derivative. So the question here is, can I replace this second derivative with something that is only defined in terms of the function? And the question is yes, because we actually formulated this in the last lesson. So for the forward finite difference, we got this expression for the second derivative. So what I'm going to do is I'm going to take this expression and I'm going to plug it in here. And we're then going to get this expression for the forward finite difference. Now, the first thing that you notice is that the forward finite difference for the high accuracy is, of course, the truncation error is h squared, and that is comparative with the conventional centered. So the high accuracy forward is as accurate as the conventional centered. Now, through similar manipulations that we did up here, now we get the high accuracy centered finite difference, which I have down here. And you can see that the truncation error is directly proportional to h to the fourth, and as opposed to the conventional centered finite difference, which is to h to the second. So you can see from analyzing the truncation error, this is definitely going to be more accurate. So let me actually delete these. So what I did, and I'm going to open up the first derivative tab here. So I went ahead and actually coded in the function. So here we have negative f of xi plus 2. So that's, we add 2 of the step size here. We have xi plus 1, xi minus 1, xi minus 2. So you can see a lot of the points that are used are for a technique that is centered, right? You have xi minus 2 here, xi plus 1, xi minus 1, xi plus 1. Okay, so this is already coded. So I'm going to go ahead. We're still using the same function that we dealt in previous lessons. And we remember with the first derivative, it was 3, add x equal to 1. So let's actually see. Let's actually call the function again. So I'm going to say c of d. And at 1, and let's go with the step size of 0.25. And we have 3.02 at 0.72%. So if I go back here, centered, it was in fact 0.72% for a step size of 0.25. So let's actually enact this equation, this high accuracy for centered, and see if it's going to actually top this technique, because if you remember, this technique, the centered, was by far the most accurate technique that we have up to this point. So let's see if the high accuracy is now the most accurate that we have. So I'm going to say high 1. I'm going to say at 1 and 0.25. Okay, awesome. So you can see we're ridiculously close to 3, and we have 0.13% error. That is a massive drop in error. Okay, so you can see that this definitely, by adding this one extra term in the Taylor series and going through this manipulations and creating this formula, did improve the error massively. Okay, so let's actually do the same thing to the second derivative. So now we formulated the centered finite difference formula for the second derivative. Oh, sorry, for the first derivative for the high accuracy. And also we have the forward here. There is another version for the backward that you're going to find available in your textbook. Now for the high accuracy second derivative, here's the conventional center that we developed in the last lesson. And through similar techniques, we're going to develop the second derivative high accuracy centered, and this is by adding an extra term, of course, in the Taylor series. Because if you remember, with the second derivative, we added up to the second derivative term, but with the high accuracy, we're not going to add one term. Through similar techniques like we did here, we end up with this formula that we have down here. So let's actually go ahead and see how it's going to compare to the most accurate formula that I have for the second derivative now, which is the conventional center that we developed in the last lesson. So if I do a centered finite difference and _2 for second derivative, and I have 1, 0.25, so we have 3.26% error, and if I go to the second, it was in fact 3.26% error. And I already went ahead and coded in the function. It's a very simple function to code in here, so very similar to what we did with the others. So I'm going to go ahead and call this, and I called it high 2. So I have at x equal 1 and 0.25. So so if you remember, the second derivative x equal 1 was 1, and dramatic improvement. So we went from 3.26% error to 0.68%. That is a dramatic drop in error. So you can see where the name of these formulas come from, the high accuracy finite difference formulas. So now this concludes a lot of what I want to teach you in terms of Taylor series and the approximation of derivatives. So we learned that with to approximate, now we call them the conventional finite difference formulas. For the first derivative, we have the forward, we have the backward, we have the centered. And for the second derivative, also the conventional finite difference formulas for the second derivative, we have this formula for the forward, backward, and centered. And of course, we compared how they perform with each other. And we came up with the conclusion that the centered is always the most accurate, whether we're dealing with the second derivative or the first derivative. Now, with the high accuracy formulas, we decided to add another term in the Taylor series, and through manipulations, we came up with a more accurate formula. And we saw this by comparing the errors. And we did this as well for the second derivative. So this really marks the end of this lesson, and I will see you in the next lesson.